Okay, so this is Ed Puzzles Unit 1 Day 1 video. So this is your very first one so you can see the layout. I'm going to make this a little bit shorter than anticipated only for the fact of I want you to get used to the layout and see how it's going to work with the embedded questions and everything. Okay, so let's go ahead and begin. It says find the x and y-intercepts and domain and range and sketch the graph. Okay, so what I have here is I have a rational function at first glance. Okay, I see the x squared, I see the x on the bottom. I'm going to think that this is rational function, but my first immediate strategy, because I do not have a calculator, is to factor. Because when I factor, I'm able to cancel out this removable discontinuity that exists at x is equal to 3. It's a hole in the graph right here. Okay, so I factored out x minus 3 and x plus 2, and I canceled out the x minus 3, so my removable discontinuity exists at 3. Okay, so this is my graph, and if you're wondering how was I able to graph this, it's basically whatever's left over after you've canceled, that's essentially the graph. Okay, and that's the graph everywhere that is not as far as x is equal to 3. So everything that's not where x is equal to 3 as far as that removable discontinuity, everything else is basically what the graph would be. Okay, so keeping that in mind. So what is our x-intercept? Well, when I'm looking for my x-intercept, my strategy is to plug in y for 0. Okay, if I'm plugging in y for 0 on a rational function, and I know this is a linear with the removable discontinuity, but at first glance, this looks like a rational function. It's the same as saying basically my numerator is going to be 0. Okay, so when I'm looking for x-intercepts, I'm looking for when does it cross the x-axis. So I'm setting the top equal to 0. Mind you, setting the top equal to 0, I'm not going to account for this 3 because we've already distinguished that as a removable discontinuity. So the only thing left over is that x plus 2 factor that you see me set equal to 0. Solving for that will give you x is equal to negative 2 or negative 2, 0 as a point. Okay, remember, these are the only ones that I'm accepting as far as how you're going to show the x-intercept. Okay. Um, for y-intercepts, I'm going to put x is equal to 0. So that's the easier one. If I just plug in 0 here, here, and here, I'm going to have negative 6 over negative 3. It gives me a positive 2. That's why my y is equal to 2 is my y-intercept. Otherwise, as a point, 0, 2. Finally, the domain is basically everything that is existing. Okay, the only place that doesn't exist that we said was here at this removable discontinuity of 3. That's why here we'll put the domain from negative infinity to 3, open on both, and then from 3 to infinity, open on both. Again, because it does not exist. Another way that we can show the domain, and we discussed this in class, is just x is not equal to 3. That means it's going to equal everything else, just not 3. Okay, so I would prefer this interval notation, but you're more than welcome to write it just like this if you want. X is not equal to 3. Okay, so range. The range is a little bit different. I mean, if I'm looking at this and I know at x is equal to 3 does not exist, well, what would it want to be if I did put in 3 in the remaining piece that was x plus 2? Okay, so if I did put in on the remaining piece x is equal to 3, I would have 3 plus 2. It would yield an answer of 5. So basically, I could say the range are all these y values except that 5 and then everything above that. That's why I have negative infinity to 5, union 5 to infinity, open on all. And again, I can say this the same way by saying y is not equal to 5. Okay, so let's go to our next example. Our next example is, again, not using the calculator. Okay, so no calculator, and we have a square root function. From parent function transformations, I know this is going to be a horizontal shift 3 units to the left. Again, because everything with x, we do the opposite. Okay, so if it's shifting 3 to the left, this is my graph already. X-intercept, the same strategy applies. If I'm looking for the x-intercept, I'm plugging in y is equal to 0. And you see me solving for it. I squared both sides to get to here. And then I just subtract 3 from both sides so that I get x is equal to negative 3, or again as a point, negative 3, 0. So y-intercepts, again, the same strategy, x is equal to 0. That's the easier one. Just plug a 0 in, and you get y is equal to square root of 3. Now, I know it's a no calculator, but if you did have a calculator, this is that decimal equivalent. Now, I don't expect you to know that, but basically I'm just showing you so that it's scaled to graph. Okay? So the domain. The domain is easy in the regards of being able to look at the picture and say it's negative 3 to infinity. Closed on the 3 because it exists as a point, and then open on an infinity because you'll never reach. And the range the same way, from y is equal to 0 all the way to infinity, because that's where the graph is going to exist. But let me show you a shortcut that you should know just with rational functions. Despite whatever you have outside of the rational functions, you could have a lot of other stuff, like negative 2 times x plus 3 underneath the square root plus 5. Whatever you have on the outside, it doesn't matter. It all matters as far as what's in the radicand. And the radicand is basically the stuff underneath the house, if you will. So we would take x plus 3 and we would set it greater than or equal to 0, and then we'd solve for x. So when we do that, we're just going to subtract 3, so we get x is greater than negative 3. Again, that's what we got over here. And we could see that quickly by looking at the graph and using what we know of transformations. Okay? Just, the graph is good, but a lot of times you'll see in AP that the graph isn't justification. Algebraic justification is what they're looking for. All right, so let's go to the next one. Okay, we discussed this in class. At first glance, it does look like a square root function. But when I'm going to square both sides, what gives it away is that it's not going to be a square root function, is this x squared term underneath the square root. Like if it was 25 times x squared, then we could cancel that out and we'd have 5x. But this is a binomial. This is not a multiplicative monomial that's listed in the radicand. Okay, so we squared both sides and we're able to get this thing right here. This manipulation yields that it's going to be a circle with a radius of 5. You see that. That is r squared. Now, something we have to remember is that when we're looking at the original function, we want to look at what is the sign in front of this square root. Because of the fact that it's positive, that says all y values are going to be above the x-axis. That's why you only draw the top half of the circle. Now, if it said plus or minus here, then you would draw the entire circle. Likewise, if it just said minus, you would draw the bottom half of the circle. All right, so let's keep going. X-intercept, again, y is equal to 0 and solve for x. You see how we squared both sides to get here. We added x squared, and then we take the square root. This step right here is very, very important. It's very commonly missed. When I take the square root of an integer, it's the positive and the negative of whatever that integer is. Basically, it's the square root or any even odd power that we're rooting. So if it was a fourth root, because of the fact that it's even, we'll have a positive and a negative. We'll have two answers. Okay, so you see x is equal to positive and negative 5. Those are my x-intercepts. Okay, so y-intercept, again, the easier one. You plug in 0 for x, and then you just solve. And then you get y is equal to 5, or you get 0, 5, which is right here. And then the domain is, again, looking at the picture, or we could set it greater than or equal to 0. Here's that trick that I showed you on the last slide. I'm setting that radicand greater than or equal to 0, and I'm solving. So then when I take the square root, watch this. This x squared is less than or equal to 25. When I take the square root, I told you up here, you would have a positive and a negative answer. Here's your positive and here's your negative. Notice, it's very, very, very important, when I got the negative, my inequality flips. This says x is less than or equal to 5, and it's also greater than or equal to negative 5. So here's the picture that you should be visualizing in your head. Greater than or equal to negative 5, and less than or equal to 5. So again, you could write it just like interval notation and just have negative 5 to 5. Okay, so let's go to the next problem. Okay, so absolute value functions. A lot of people they're not used to doing algebraic manipulations with these. The thing that I will basically give you the premise of is if I take the square root of a negative number, I'm going to get its positive. And if I take the square root of positive, I'm still going to get the same thing, the positive. Okay? So basically what I'm saying by this is that this original equation can be written in the negative form and in the positive form because of this interpretation up here. These x's will cancel and I'm left with negative 3. These x's would cancel and I'm left with positive 3. That gives us positive 3 and negative 3 as far as where our graph is going to exist. Okay, so we can basically say, yeah, there's going to be a line here and there's going to be a line here. We're going to see how it restricts here in just a bit, as you see it restricted here already. X-intercept. Again, set y is equal to 0. So we would set y is equal to 0 here. And we're doing it over here. So 0 is never equal to negative 3. Nor is 0 right here ever equal to positive 3. Because of that, you'll have no solutions. There aren't any x's that you can solve for. Okay? Another good helpful hint is the fact that when I'm looking over here, I have a discontinuity. It almost looks like a vertical asymptote, but again, this was a form of cancellation that shows it's not going to be a a vertical asymptote. These are canceled. It's going to be a form of a removable discontinuity. In this case, a jump discontinuity. Okay, so if I go to Y-intercept, plugging in x for 0, this is going to be an undefined answer. The reason of it being is it's not really a no solution, it's an undefined, because any error that I'm ever getting when dividing by 0 is going to always give me an undefined. So let's look at the domain. Okay, the domain on this graph, as you can see it already drawn, is obviously negative infinity to 0, which is that point of discontinuity because of that removable jump discontinuity. And again, you could write it like x is not equal to 0. And then the range, you could write it as y is equal to positive or negative 3, or you can write it as the set of these y's. So these are independent elements, basically. Y is equal to negative 3, and y is equal to positive 3. Now, here's a question that a lot of people ask. Well, how did you know that this was going to the right and not the left? And how did you know this was going to the left and not the right? Well, a simple way to see that is just to plug in some test points. So for instance, if I plugged in, let's say, positive 2, and I plugged in positive 2 over here in the original equation, I would have positive 2, this would be a positive. So that shows it's going to be in that positive direction, okay? Or basically greater than 0 direction. And if I did another test point like this one over here as negative 2, I'd have the absolute value of negative 2 is 2. I'd have that multiplying with 3, but then I'd have it dividing by negative 2. This gives me a negative answer, a negative realm answer, if you will. That's why this is going to go off to the left over here. That's how you know. Okay, it's going to be either what you see drawn here or vice versa. All right, so let's keep going. The next one says sketch the graph. Okay, so the given pieces that we're given are basically of a piecewise function. We have function 1 and we have function 2. Let me highlight them and actually color code them so that you can see what they look like. So this 1/3 x minus 2 has a y-intercept of 2, and it's over here going to the right with the slope of 1/3. Up 1 over 3, up 1 over 3. Okay, this one over here is x squared minus 1. Now let's think about this. The way I drew these quickly was that I interpreted this as a parent function of x squared, and I shifted it down 1. And then up 1 over 1 gave me that next critical point, and then everything just went from there. But I'm only drawing because of this bounded domain region of x is less than or equal to 0. And again, here's your visual if you need it. I'm only drawing to the left and including 0. You see how it's closed here. And then the next piecewise function, like I said, it would be the entire line, but we're only going to draw this greater than 0. So it's open at 0 and everything to the right. And again, here's another number line visual for you so you know which direction you're graphing. So here's the thing that I tell my students every year. When you are given a piecewise function and you see this less than or equal to 0, and this one's greater than equal to 0, or sorry, greater than 0, they share that commonality of 0. So let's say if x equaled 0, what would happen? So if I put 0 here, essentially, I get a point that is 0, 1. Or sorry, 0, negative 1. If I put 0 here, I'm going to get a point that is 0, negative 2. Those are basically my accurate points so that on the graph, I'll know exactly where they're at. Because if I don't do this, I don't know whether these two would actually intersect. I don't know whether they're actually going to come from the same point. And like this 1/3 is actually up here. The best way to do that algebraically without having a calculator and without actually having to draw the graph is to do this right here and see that they're not going to share. And we'll talk about that in the next unit, next couple of units when we're talking about continuity. Okay? Okay, so let's go to the next problem. The next problem says find the asymptotes. The horizontal, okay, so the horizontal, the vertical, and then the slant. And it also says symmetry, intercepts, and then sketch the graph. Okay, so again, with no calculator. When I look at the original function, it does look rational to me. So with rational functions, my first go-to is factor everything, top and bottom, independently. And I see that there aren't any removable discontinuities that will cancel, but I can go to my x-intercept simply by setting the y value equal to 0, i.e. what we talked about before, setting the numerator equal to 0. Okay, so I divide by 3, I get x squared is equal to 0, then I square root both sides, and that's how I get x is equal to 0. So therefore, if I plugged in 0 into this function, it's 0 over negative 4, would yield a y value right here of 0. So if I put it as a point, it would be 0, 0. If I put it as just an x-intercept by itself, it'd be x is equal to 0. And again, this x is equal to 0 is talking about that guy right there. Okay, so let's come back. Let's now look at the y-intercept. Again, this is the easy one. Just plug in 0 for x. So 0 over negative 4 is going to give me 0. That's y equals 0. And that came from putting in this value of x is equal to 0 right there. So again, I could do it the 0, 0 point or y is equal to 0. So there's my x-intercept and my y-intercept. So the VA. Remember from pre-cal, anything that did not cancel in my original rational piece is basically on the bottom set equal to 0, and independently those are my vertical asymptotes. So I have a positive and negative 2 based off of just solving the bottom either here from the original or just looking at the factored form. A lot of times I just look at the factored form because it's a lot faster. So we have positive and negative 2. And you see those here, negative 2, and then you see the positive 2 VAs drawn. Okay, let's go to our HA. I'll tell you right now, HA and slant asymptotes, you will have one or the other. If you have an HA, you will not have a slant or anything under this category. But if you don't have a horizontal asymptote, you can and will either have a slant or a quadratic or a cubic. It depends on how much difference is the top degree from the bottom degree. In this case, they're the same. We'll discuss what that means here in just a bit. But like if the top was x to the 4th and the bottom was x squared, well then you would have a difference of just 2 degrees. So your asymptote would be a form of some kind of quadratic. Instead of this line here that's horizontal, or a slant line, like if it was like this. Slant line would come from something that would be like x to the 5th over x to the 4th. Whatever they are, they're just one number apart. Okay, so now let's go back to see why this is a horizontal asymptote. So the acronym Bobo-Botnitz's ratio. It's an easy way to find the horizontal asymptote. And I did tell a couple of classes, I can't remember which classes, but an easy way to remember this is like clowns, they make you laugh. So ha ha ha, they make you laugh. There's your horizontal asymptote. I know that's a little corny, but hopefully it works. So horizontal asymptotes, you're going to use Bobo the clown, Bobo-Botnitz's ratio. So this means bigger on bottom, y is equal to 0. That's what the acronym stands for. Okay, so let me get a different color so it doesn't cover it too much. So when the exponent is bigger on bottom, y is equal to 0. So in this case, my original exponent is x squared, and my biggest exponent in the denominator is x squared. So they're the same. Okay, so this one is exponents are the same. What is the y value horizontal asymptote? It's whatever the coefficient ratio is, which is, in this case is going to be 3 over 1. That's what we have at y is equal to 3, our horizontal asymptote. Now the last part, you're basically going to graph from using something called the sign test. Okay, the sign test. You just want to see what signs will these have if I do certain test points, if you will. Okay, so here comes the question. Where did I get negative 2, 0, and positive 2? These critical points come from the zeros of the function that's setting the top equal to 0 and solving for x, and from the discontinuities of the function. That's either the removable or the VAs. So setting the bottoms equal to x, I get -2 here, and I get +2 here. Those are my points that I'm basically going to test everything else outside of that. 1, 2, 3, 4 intervals. Okay, so I'll just ask you, pick a number, any number that is less than -2, over here somewhere. So let's say we pick -3. So I would put -3 in the factored piece, not the original, because the factored is more efficient and easier to see. So -3 squared, well, because it's squared, we always know that that's going to be positive. So it would be positive on top. And then we'll say -3 plus 2 is -1. But we don't care if it's 1, we just care that it's negative. And then -3 minus 2 is also negative. So what is this multiplicatively equal to? Well, positive on the bottom, because negative times a negative is a positive. Positive divided by a positive, that's where we got what's already written here for you, this positive piece right here in that first interval. Okay, so that's where it comes from. It's the sign test. So if I tried other points, like here, if I tried 1, plugging it here, here, and here, I would get signs that equaled a negative. If I did +1 here, and I tested all the points, I would get a sign that was equal to negative, and then finally I would get one that was equal to positive. What this tells us is that from -2 to the left, it's going to be positive. Now, we cannot draw a graph here because of the fact that right here we will go negative. And it must be positive, everything less than or equal to -2. Actually, less than 2 because that's the VA. So everything less than -2, it has to be positive. That's why the only place where it will both approach the VA and the HA is going to be if it's in this top left-hand corner, if you will. Okay? So now let's go ahead and go to the second one. From -2 to 0, we have it negative. And that shows that from this x and y-intercept, I'm going to approach that VA going into the negative realm. So from 0 to 2, I will approach from this x-intercept, y-intercept, also to the negative realm, as I'm approaching that 2. And then finally, positive. And this is the same thing like this first piece was. It's going to be positive because for all this entire interval, it's always above the y-axis. It never goes below the x-axis. Okay? So x-axis, I think I might have just said y-axis. I meant x-axis. All these y's are above the x-axis, so they're positive. Okay? Let's go to the next one. Oh, and the symmetry on this. The symmetry would be even. I didn't write that quite yet, but it would be even because of the fact that all outputs that are this way yield the same outputs that are if I went the other direction. So equation-wise, this is important. Let me show you what an even function as algebraically written would look like. It's basically this. So I have f of x is equal to f of -x. Now listen to what this looks like, or how you should read this. X is positive, x is negative. I just showed opposite inputs. Okay? And opposite inputs yield, kind of imagine that there's a positive f of x right in front. And over here there'd be a positive f of x. I know it's f of -x, but the fact that it's positive here shows that these two signs, and basically the y values, are going to be the same. So when I see this by itself, you should interpret opposite inputs yield the same output. And that's like reflecting across the y-axis. If I went to the right 3, I would be right here. If I went to the left 3, I would be right here. Thus saying that same y value. Okay, so it's an even function. Let's go to the next one. This right here, again, our first strategy is to factor and see if we can cancel anything. And we can't cancel anything from this factored form of the rational function. So again, my strategy for x-intercept, y is equal to 0. That is setting this top equal to 0 and solving for x, which I get 0 and -2. Or I can write them as points by plugging those that 0 and negative 2 in so that I could see that it's going to be 0 as far as your y output. But of course, that makes sense because those are my x-intercepts. Okay, so now I'm going to go to y-intercepts. Again, the easy one. Plug in 0 for x, so I have 0 over negative 1. And we all know that 0 over negative 1 does equal 0, so that's why y is equal to 0. One thing people don't know is that negative 1 divided by 0 is not 0. It is undefined. You can never, never, ever have an answer whenever you're dividing by 0. Okay, so let's go to the VA. So like I said before, anything that's not factored out as a removable discontinuity that is located in the denominator piece is going to be your VA. So x is equal to 1. And that x is equal to 1 is over here as far as my vertical asymptote over here. Okay, so let me unhighlight that just a little bit. And let's go to the horizontal. So Bobo-Botnitz's ratio. The fact that I have x squared and x to the first says it's bigger on top. So there is none. That's why the n is for Botten. When there's not a horizontal asymptote, there must be a slant or a quadratic or a cubic. It could just go on and on. There's going to be some kind of in-behavior asymptote. Because x squared is only 1 degree away from x to the first, we know it's going to be a linear function. Now, some people were asking me, if I were to do synthetic division, and I'm looking at basically dividing so I can get the coefficient, here I'm taking x squared, the coefficient of x squared is 1, the coefficient of 2x is 2, positive 2, and I have no constant term, so I'll put 0. And then x minus 1 says, if I set this equal to 0 and I solve for x, x would equal 1. This is my x-intercept. That's basically, or not x-intercept, this is my 0 of the function, which I'm going to test it here. Okay? This is what actually gets synthetically divided by the synthetic division process. We bring down the 1, and then we multiply. We get 1. We add 2 and 1, we get 3. Then we multiply. 1 times 3, we get 3. When we add, we get 3. So basically, this new placement value, like up here, my 0 is my constant. My new constant placement is 3. And then you just go up from there. So 1x, like if there was another number here, let's say that there was 2, it'd be 2x squared, and so on and so forth. Now this remainder is what people were asking me about. This remainder, you can write it like this. And notice that I put it over x minus 1, my original divisor, if you will. This isn't required, but you can put it. And the reason of it being is if you approach infinity, basically putting infinity where x is at, it's 3 divided by a very, very, very huge number, which means this would converge to a limit value of 0. Because any number divided by something that is way, way bigger on the bottom, remember, bigger on bottom, that's Bobo-Botnitz's ratio, bigger on bottom, it's going to converge to y is equal to 0. That's why this is negligible. Like, you don't even need it. Okay? So x plus 3 is this slant asymptote that you see right here. It has a y-intercept of 3 and a slope of 1. Okay, we're going to do the sign test again. And like I said, the sign test comes from the zeros of the function and from the VAs. Okay, the zeros of the function that we got x-intercepts were at -2 and at 0. And then from the VAs we got was 1. And that's also from the graph if you wanted to look. So basically I have, here's an interval, and then here's an interval. And we're going to test those points to see what are the signs on those intervals. Okay, so again, let's say that, let me get a better visual for you. I'll put it down here. So here's -2, here's 0, here's 1, and those are the only ones that you graph, because again, we only graph our zeros of the function and our discontinuities. So 0, 0, there it is, and our discontinuity is 1. So when I do test points, let's say that I put a -3. If I put a -3, again, I'm going to put that into my factored form because, in my opinion, I think that's the easier way to see the negatives. So -3, it's going to yield negative. Negative 3 plus 2, it's a negative 1. And on the bottom, it's going to be negative 3 minus 1. It's going to be negative. So negative on the numerator makes a positive, and a positive divided by a negative ultimately ends this as a negative. And that is reinforced right here with the graph because all of this negative piece is below the x-axis. If I continue to do test points on this, I would have positive, and I would have negative on this one, and then I would have positive on that last one. Okay, just doing it the same way to save time, I'm not going to do it. But I'd have positive, that's why it would be above. I'd have negative, that's why it would be below the x-axis, and I'd have positive. Now, if I did this as a graph, this isn't positive throughout the entire interval. It's showing that it's negative right here. So that's why we have to specifically go only where it's always positive, which in this case would approach not only the slant asymptote, but the VA as well, and all the while stay positive above the x-axis. Okay, so we're almost done. Solve, draw a number line graph for each problem to show how you got your answer. So you see how I factored. This is just factoring by grouping. So if you don't remember that, that is multiplying the a and the c term together to get negative 30. And then you have to ask yourself, well, what two factors can I write that will multiply to negative 30 and at the same time they will add to negative 7x? So negative 10 and positive 3 multiply to negative 30. They also add to negative 7. So that's why I'm basically replacing this negative 7x with two monomials. Okay. The reason of it being is, in case you have forgotten, so I can GCF them out in pairs. Okay. What does 15x squared and 10x share in common? Well, they share a 5x in common. What's left over after we GCF factor that out is a 3x minus 2. Okay. And then over here, nothing is 3x and 2 have in common other than 1. That's why the 1 was factored. And 3x minus 2 is remaining inside. So again, a lot of people forget factoring by grouping. Whatever's on the outside is one factor. Whatever is on the inside, and these are identical pairs. If they're not identical pairs, you've done something wrong. That's the other factor only counted once. Okay, so inequalities. If I were to treat this right here, instead of a greater than sign, just like an equal sign, and I were to solve the zeros, I would get negative 1/5 for this 0, and that's why I have it graphed over here. And then I would get positive 2/3 here. Now, these are open circles, and the reason why I left them open was because this is greater than. It's not greater than or equal to. So again, I'm just going to do sign test. So when I come over here and I do sign test, something less than negative 1/5, I'm asking myself, I can try like negative 1. And I'm going to use the factored form. So negative 1, let's plug in for x. We get negative 5 plus 4. It's going to be a negative. And I'll do negative 1 here. So negative 3 minus 2 is going to be a negative. Because when I multiply those two, I'm going to get that positive that you see written right here. Okay? If I were to do test points on these other intervals, I would get a negative and a positive. Let me show you how I would get the negative, and then you could do the positive on your own. The reason why I would get a negative in the center one is the best test point to test between a negative and a positive number is 0. So when I plug in 0 here, I get positive because I get positive 1. If I plug 0 in here, I get a negative because I get negative 2. So positive and negative, that's why we get a negative there. So our goal from doing these sign tests are basically to show where something is going to be negative and positive, because we're concerned with whenever, according to the original equation, when is it positive? When is it greater than 0? You can see that here too. That's when it's greater than, and that's when it's greater than. That's why we have negative infinity to negative 1/5 open, because of the fact, again, that this was non-inclusive, and then 2/3 to infinity. Okay, let's go to B. What I did with B is I subtracted 12x to both sides so that I get 0. I GCF'd out an x, and then I factored that trinomial so that I have 0 as a 0 the function. I have negative 4, and then finally I have 3. Just like I did over here in this other problem in part A, I would do the sign test so that I can see when is this function less than or equal to 0. So we want to know when is it negative, because that's our domain of answers, if you will. So negative infinity to negative 4. Again, I have a bracket this time for the fact of this bracket shows it's closed interval. It's inclusive. Union 0 to 3. Closed and closed. All right, so let's keep going. Almost done. All right, so drawing a number line. Here we can see 0 is already by itself. Again, I can treat this inequality sign like equals so that I can quickly find the zeros that I'm looking for. This is negative 3/2 from here, and this is positive 4 from here. Again, less than says they will be open. Okay, so both of these are going to be basically open intervals. Doing the sign tests, like if I were to do negative 2, because this is negative 1.5. So we could do negative 2, we could do 0, and then we could do like 5. And doing it just like we did the other problems, you would see that you'd have a positive, positive, and negative. And because of the original equation, the way it was asked, we wanted less than 0. So we wanted the negative answers. And that gives us 4 to infinity, open on both. All right. So this right here is also similar to what we just did on the last slide. We're drawing a number line and we're showing that. So you see up top, this was factored out to x minus 5, x minus 4. The bottom was a difference of squares. So I have plus and I have minus. Nothing cancels. So looking at this, the zeros on the top are 5 and 4. Again, what goes on this number line? Well, the things that go on the number line are the zeros, otherwise known as x-intercepts, or the VAs, or the removable discontinuities. Any form of discontinuity and any zero of the function, basically x-intercept, those are all the candidates that go on my sign test, if you will, my number line sign test. Testing all these, here's the catch. I have a 3 and I have a negative 3. Those are non-inclusive because those are my VAs. So at 3 and negative 3, that's why I have my parentheses. Okay? And at 4, something's going to exist at 4. And also at 5. That's why they're closed. Okay? So let me go ahead and do that on the graph. These would be closed. And that's why you see the brackets located down here. Okay? So looking at this and doing the sign test points, you would see that you would have negative infinity to negative 3, 3 to 4, and 5 to infinity. All right, the last one. This is another factor by grouping, where I basically have 4 pieces, and I group them into 2 pairs, and I factor their GCFs. So x cubed, 3x squared. What's the GCF that they share? Well, it's x squared. What's left over after I divide out x squared from x cubed? Well, x. And over here, 3 is left over. So over here, all I did was factor out a negative 4 so that I could get that x plus 3. So I'll tell you, from my experience, this one's the easier one to get. And if you're doing it right, try to make the second one match the first one. Okay? Then you'll have x squared minus 4, which is on the outside as one of your factors. And you'll have x plus 3, which is your 2 of a kind, only written once. Finding the zeros, we have plus and minus 2 for the first one. And then we have negative 3 for the last. Again, the same process. We want to look when it's positive. So positive, positive. These have no VAs whatsoever or discontinuities of any kind. It doesn't error out because you're dividing by 0 the way it did over here on this last one. That's why these are going to be closed, or sorry, these are going to be open, sorry. These are going to be open because of the fact that also this is greater than. It doesn't have a greater than or equal to. Okay? So these are open, and I'm only going to look at when is it greater than 0. When is it positive? And you see that negative 3 to negative 2, open, open. And then 2 to infinity, open. Okay? So let's now come over here, and this is our last slide. It says write a piecewise function for the following graph. You see here from the graph I have negative 2, positive 2. I have negative 4, positive 3. From here I can do y's basically delta y over delta x, or y2 minus y1 over x2 minus x1. You learned it in Algebra 1. And this is your slope. It's negative 1/2. So my y-intercept from the picture is 1. So that in y-intercept form, or slope-intercept form, my y equals mx plus b, I have negative 1/2 x plus 1. This is the first function on this piecewise that I would draw. And you see that it's restricted everything from negative infinity to 0, closed on 0. That's what we draw our domain, or write it like this inequality form here. X is less than or equal to 0. The red graph, this is a parent function coming from x squared. Again, it looks like it's shifted down 1 from what we know of our vertex and this critical point to the right of up 1 over 1. And its domain right now looks like it's greater than 0 and goes off to infinity. So I would write the function here. That's where your f of x goes. And then your domain restriction comes over here. X is greater than 0. All right. I hope you enjoyed the video. The other one will come soon, but this is all we have for day 1.